I will talk about my master thesis, and it was line profile variability in galactic B supergiants. So I took a sample of B supergiants and studied its line profile variability. B supergiants are evolved massive stars. They're slow rotations, and they have very high values, usually of macroturbulence. Macroturbulence is additional line profile, line broadening. It has been connected with stellar pulsations in last few years. So it is also said that number of pulsating frequencies can be very high, more than 10 or so. Analysis of pulsation frequencies can help us differentiate B supergiants from the stars in the blue loop. So it means that when star gets from the main sequence and onto the blue supergiant region, it goes then to the red supergiant and then goes back to the blue supergiant. So these are the stars that are in a blue loop. It's very, very difficult to tell between these two types of stars because they have a similar place on the HR diagram. Yes. So I will talk. So during my master thesis, I studied the line profile variability of H alpha and of photospheric lines. So photospheric lines in B supergiants show difference in variability in radial velocities, and this variability is due to stellar pulsations. So pulsating stars are type of variable stars which change in radius and the shape of the stars. So the change of the radius doesn't have to be radial. So it means that only the star expands and contracts, but it may expand in one place while contracts in the other. So the change of shape is not so symmetric anymore. So we call this difference radial and non-radial pulsations. Through the stellar evolution, the stars may stop and start pulsating several times. So they can go through several instability domains, enter and exit. And what is very important that from these stellar pulsations, we can study a lot of stellar parameters. We can backtrack age, mass, chemical abundances, convection zones, internal rotation, and other things at time. So the kappa mechanism is responsible for driving the stellar pulsations. So the one layer of the star, because of the opacity of one element, the radiation cannot go through anymore. So it builds up under this layer and it pushes it forward. So the layer pushes forward and it okay, cannot remember the word. So the layer contracts, and so when the layer contracts, the temperature goes up, the opacity goes up, and the pressure in the layer builds up. And then as the layer expands, it starts, the radiation starts going more freely through it. So opacity goes down and temperature goes down, and the pressure on the layer now increases, so it can go back to its previous position, and the layer falls inwards. So, and then it starts the cycle again, so it's the kappa mechanism. So I was talking about this, that pulsation are helping us distinguish these evolutionary phases. So on the first graph on our left, we can see the pre-red supergiant phase, and we can see that we can see on the upper panel, we can see two evolutionary tracks for two stars with different masses. And as it goes to the red supergiant stage, we can see the number on the lower panel. We can see the number of pulsation modes excited. And we can see that there is, well, on the right panel, we can see the after red supergiant stage. And we can see that there is a lot of more pulsation modes excited. And so they're also different. They're in post-red supergiant stage, we can see also strange modes. And before red supergiants, we can see radial and non-radial. So it kind of helps us differentiate. So how we did analyze our data? We wanted to connect macroturbulence and line profile variability, or the variability in radial velocities, together with pulsations. So we would look for macroturbulence during FFT method for rotational velocities, and we would use moments method and then Lomskargal period analysis on a time series of spectra to investigate the line profile variability, and then we connected this together to get to obtain confirm there is a pulsation period present in a star. So I will show one of our results because I thought I would not have more time. So this is Sigma Cygni, or HD22850. It's a silicon-rich star, which is indicated that it's in a post-red supergiant phase. From the literature, we know it has a high value of macroturbulence. And on a series of, we had a 4-time series. And on all 4-time series over 2 years, we could identify 1.59-hour period. And we derived it both using Fourier transform period analysis and simple sine curve fitting. So we can, on the panel, we can see the first 3 moments. So the first moment, it's on the top panel, the first 3 pictures. They show a variation of radial velocity. We can see that in phase, so it's versus phase. So we can see that the variation is the same for 3 lines. So we investigated silicon 2, lambda 6347 and lambda 6371, and helium 1 6678. So we can see that all 3 lines vary in phase, and that the first moment and the third moment vary in phase as well. So we can say that this is a signature of pulsations. And conclusions. So the most important result of my master thesis I just talked about. It's the 1.59 hours pulsation period. And also the star is not in any known instability domains. And even for B supergiants, it's a very, very short period, so it's not expected. All our stars, they show large line profile variability. And we also showed that there is macroturbulence present in each of our objects, as well as that the FFT method for determining rotational velocities is not reliable in these objects. So that would be all. Thanks for your attention.
Thank you very much.